Alright, so chapter 10 is about states of matter. We're going to go into gases, liquids, solids. We're going to look at changes in states of matter. And just some stuff you've probably seen before, but we're going to go deeper into it. For instance, with the kinetic molecular theory here, looking at how molecules, they tend to be in motion. You know, we're used to thinking things like a solid is just sitting there, but really, according to kinetic molecular theory, you can picture it as a bunch of tiny molecules that are actually vibrating. They have a vibration. So we're going to look at the 5 assumptions of that kinetic molecular theory in terms of gases. Then we're going to look at some properties of gases like expansion, density, fluidity, compressibility, diffusion, and effusion. And then finally, we will compare an ideal gas to a real gas. So kinetic molecular theory is based on the idea that particles, like I said, they're always in motion. We can think of the classic diagrams we see of solids, liquids, and gases, how those particles are in a little bit of motion. And this theory can explain some properties of solids, liquids, and gases in terms of the energy of the particles and the forces that act between them. So an ideal gas would meet all of these assumptions perfectly. In real life, not all gases are going to do that, but ideal gases, assuming that gases are ideal, helps us to realize or to make calculations and things that we wouldn't normally do or be able to do if we had to worry about all these little factors that could play if we were looking at real gases. So the 5 assumptions we have, the first one, we assume that gases consist of a large number of tiny particles that are very far apart. So they're not necessarily like bumping into each other and reacting to each other. Like if I said, I want you to go down to the office, it's going to be a lot different if you're just walking there right now versus if I said that right in between class changes, right? Because if it was in between classes, you'd be bumping into everybody, you'd be slowed down by people. But with ideal gases, we're assuming that everybody's so spread out that you have a nice, even walk to the office versus the crowd that you would expect between classes. And also, we do assume that collisions will happen. Collisions are going to happen between gas particles, just like they might happen if you're out there in the hall. But when they do happen, that's why I brought the Newton's cradle out. If you don't know what a Newton's cradle is, Newton's cradle. One of these things where you have, one side hits and then bounces the other one along. That's a Newton's cradle. And this one on the screen is going to go on forever, right? There's nothing stopping it. Those are what we call elastic collisions because it just keeps bouncing off. In real life, the real Newton's cradle only lasts so long and it eventually runs out of energy. That's actually a good analogy for this one on the screen would be an ideal gas, and then the one in real life would be a real gas. And it's not like they're totally different, right? I could probably make some observations on that one that are similar to this one, but because of the friction and other factors involved, maybe they're not hitting it just the right angle because it is kind of an old Newton's cradle. You might not see this satisfying thing happening forever. So that's kind of what we're saying is a real gas pretty much acts ideal, but there are some properties that we ignore, and elastic collisions is one of those. So that example of an elastic collision where no energy was lost, that would be like a Newton's cradle. In any elastic collision, by the way, if you take physics next year, you're going to learn that would be where energy is lost. So something like a car crash where the two cars stick together, that would be an inelastic collision. Or any collision where energy is lost. A third assumption we're going to make is that gas particles are in continuous rapid motion, random motion, and they do have kinetic energy. Another physics-y concept, that energy of motion. So you can see kinetic energy actually has an equation, Ke equals 1/2 mv squared, meaning that we can determine the kinetic energy of a particle if we take 1/2 times its mass times its speed squared. The temperature depends on the average kinetic energy of the particles. So each of those particles of a gas might have its own mass, it might have its own velocity, but the average of all the kinetic energy is what will help me determine the temperature. So the higher the temperature, the faster those molecules are moving around. The lower the temperature, the slower they're moving around. And finally, this kind of goes along with this first assumption, but there's no forces of attraction between the gas particles. Oops. One thing we want to note about kinetic energy is that at the same temperature, all gases have the same kinetic energy. So, if we're looking here, we know our formula is Ke equals 1/2 mv squared. Let's just compare two gases. Let's say oxygen and hydrogen. Do you know off the top of your head what oxygen's molar mass is? 16 for 1, so if I had 2, it'd be 32. And then hydrogen is 1, so it's going to be 2. So obviously 1 is much more massive. Oxygen is the more massive one, right? So one has a large mass, one has a small mass. Based on the fact that they both have to have the same kinetic energy if they're at the same temperature, which one of these two is going to be moving faster? If I have a large mass versus a small mass, which one would have the higher speed, the bigger one or the little one? Yeah, the little one, because it has to match. They both have the same kinetic energy, so as speed goes up, velocity goes down. Or I'm sorry, as mass goes up, velocity goes down. As mass goes down, velocity goes up. So you see that here, lighter gas particles will have higher average speeds, so therefore hydrogen would have a higher average speed than oxygen. At the same temperature, that is. So again, that kinetic molecular theory only applies to ideal gases. And we usually see ideal gases as long as the pressure is not super high and the temperature is not super low. So let's look at some properties, the first one being expansion. Gases don't have a definite shape or a definite volume. That's why if I opened up some, or sprayed some perfume, you had that vapor. Eventually, everyone in the room would smell that, most likely, because the gas will expand to fill the air, or to fill the room. So gases completely fill any container in which they're enclosed. And they also rapidly move in all directions, so that without significant interaction. So if these gases are moving randomly at high speeds, as you can expect, they would spread and spread and spread until the whole container was filled. A second property we're going to look at is fluidity, because we can ignore those attractive forces between gases. They will easily glide past one another. And one thing that people don't realize sometimes is that gases actually classify as a fluid. Fluid just means that they flow past each other. So liquids and gases are both fluids. Gases also have very low density. You guys know what solid carbon dioxide is? It's not super common, but I'm sure you've encountered it sometime in your life. Max, do you have any idea what solid carbon dioxide is? It's okay if you don't. It's dry ice. Like if you ever ordered like something cold online, sometimes they'll pack it in dry ice and send it. So that's the solid form of carbon dioxide. That's what the particles very densely packed together. If we have the gaseous form of carbon dioxide, that's 1,000 times less dense than that solid form. So because it's so not dense, we can compress it very easily. There is a point to where it becomes difficult to compress, but like if I had a syringe with gas inside, you can press in pretty decently before it starts to press back, because those gas particles are so far apart, we can compress them together. Liquid is, believe it or not very compressible. If you have something filled with liquid, it's going to be very hard to make the volume of a liquid smaller. Same with solids, unless there's a lot of air in between. Finally, we're going to look at two other properties of gases, diffusion and effusion. Again, we don't need to stir gas in order for it to expand throughout the room. It's going to spread out and mix. Two gases are going to mix with each other because of that random and continuous motion. So that's when I just have gases spreading throughout a container. That's called diffusion. Whereas effusion is when gases pass through a tiny opening. This just reminds me kind of like if you blow up a balloon, don't tie it up, let it go, and it floats all around the room. That's the gas escaping through a little tiny opening, which is propelling that balloon. So that's a fusion. But any time that gas is passing through a tiny opening, we call that a fusion. And one thing to note with our kinetic energy, like we said, low mass particles will effuse much faster than high mass particles. And we'll watch a video that shows that in a second. But I just want to make a point about real gases, that all these things we talked about, we're assuming that they're ideal. So they're not at high pressures, they're not at low temperatures. Also, the more polar a gas's molecules are, the less likely it will be to be close to ideal. So the more it will deviate or stray away from ideal behavior. So a real gas is what we're mostly encountering, but we're just usually going to make the assumption that it's an ideal gas because it makes our life a lot easier. So let me show you this diffusion idea. There's actually a law called Graham's law of diffusion. And I want to go back to that demo. I think I had it here. This one. This one's good.
So I'm going to start with ammonia and hydrochloric acid. And I'm going to start with the heavier gas. Hydrochloric acid is 36 grams per mole. So real quickly, I am going to add some hydrochloric acid to my cotton.
So let me just set this up. Well, actually, I'm going to let it play while I'm talking about this.
All right.
So he's going to put a little bit of ammonium hydroxide in the cotton ball on the left, and he's going to put a little bit of hydrochloric acid on the cotton ball on the right. NH3 has a molar mass of about 17 grams per mole. HCl has a molar mass of about 36 grams per mole. So what's going to happen is they're going to vaporize when he shoves them in each end of this tube, And when they meet, they're going to form a precipitate called, it's going to be ammonium chloride, and it's going to make a white smoke when they meet. So when the two gases meet. It's going to take them a little while to travel down the long ends of the tube. But my question for you is, would you expect the two gases, again, this one on the left is lighter, the one on the right is heavier. Would you expect them to meet closer to the left side, or closer to the right side, or straight in the middle? Do you agree? All right, we'll let him finish this out and see if you're right or not.
You can see that
It's a little wobbly
that
there.
line. So right now, the faster gas should be meeting my slower gas somewhere in the middle here. All right? Just make sure my tops are on. We're going to wait a few minutes and come back, and I'll show you that line. So after 15 minutes elapsed time, we look and see that there is clearly the interface between the two gases. And that interface, okay, where these two gases are meeting, is creating that white, cloudy smoke, which is the ammonium chloride. You can see that smoke proliferating right there. If I pull back, keeping my focus a little bit, you'll see that that is clearly on the hydrochloric acid side.